So what if we have a curve that does not have uniform curvature like a circle? Well, we can still figure out the curvature, but I'm actually going to use a different formula for it. So let me go back really quickly because I realized as I was doing this that I forgot to mention what was going on here. So for this, we could take our direction vector, i.e. our velocity vector, cross product with our acceleration vector and divide it by the magnitude of our velocity vector. So if r is position, I guess I should make a little note. V is velocity. This is position. V is velocity. I'll just make a note over here. V is your velocity vector. And A. I meant to talk about it and I forgot. So acceleration. All right. Get rid of that right there. All right, so let's use this for this particular one. Not that we couldn't use this other method because we could, but just to, that way you've seen both formulas getting used. So let me go back here. So I found my first derivative, as you can see, and that would be velocity. So this right here is my velocity vector, because if this is position right here, which is my r of t, then the derivative of position is velocity. Oop. Apparently I wrote the last of the word acceleration on another sheet of paper. My fault. Okay, so now what? I need the acceleration vector, but acceleration would be the second derivative of position. So that would be here, r double prime of t, which is 0 to 0. And that's my acceleration vector. Okay, I'm going to need the magnitude of my velocity vector. That's just part of it. So I might as well figure this out because that's in the denominator. So if you look, I'm going to need the magnitude of my velocity vector because I'm going to need to cube it. So I might as well figure out the magnitude of my velocity, which is the magnitude of my r prime. Which would be the square root of 3 squared plus 2c squared plus 1 squared. Which would be the square root of 9 plus 4t squared plus 1, which would be the square root of 10 plus 4t squared. Or if you like 4t squared plus 10, I mean, it doesn't really make any difference. Okay, so there's the magnitude of my velocity vector, which is the derivative of my position. Sorry, my R is looking really strange there. All right, next, let's find the cross product because that's the numerator. So I'm going to need the cross product because I'm going to need the magnitude of that cross product. Okay, so let's find the cross product. So I need V crossed with A. I, J, K. V was 1, 2, and, or excuse me, sorry, I'm getting that wrong. 3, 2t, 1. And then this was 0, 2, 0. Cross product. And again, I'm going to use a little trick. I, J, put a 3 and a 2t here, and a 0 and a 2 here. Luckily, all those zeros mean most of the things disappear. There's no I component. There's no J component. There's 6K minus, there's no K in the negatives. There's an I, so 2I, and no J. So that means that it's negative 2, 0, 6. That's my cross product. Okay, so now let's use all of these pieces to go find kappa. So this is all kind of work that we did ahead of time. So kappa is the magnitude of the cross product V cross A over the magnitude of V cubed, which is going to be the square root of negative 2 squared, 0 squared, and 6 squared, right? That cross product, divided by, now I actually already found the magnitude of v, so that was kind of nice. So square root of 10 plus 4t squared. I mean, otherwise you'd have to find it now in the Kappa formulation, which is fine. I was just trying to get rid of a couple things. So that numerator, that's 36 and that's 4. So that's the square root of 40 over 10 plus 4t squared to the 3/2. It's just easier that way, which is 2 squared root of 10 over 10 plus 4t squared to the 3/2. Either one of those works, right? So these are kappa. Okay, so they wanted to find an expression for the curvature. So this is an expression for the curvature. Notice it has a variable in it because it's not a circle, so therefore it's not going to be constant. Right? It contains t because the curvature is not constant. Constant, like a circle. Right? Circle would be constant curvature, but this is not, and that's why this is not a number. This is a function. So it means the curvature is going to change depending on where you are along said curve. So to fill out the table down below and see what the curvature looks like at different points along the graph, let's actually use Maple. So this is not perhaps the most efficient way I could have done this in Maple, but it's done. So I named my kappa function. I called it K1, and it's 2 square root of 10 divided by 10 plus 4t squared to the 3/2, right? So there's kappa right there. And then I'm telling it to evaluate kappa at the different values. So t equals 0 gets me 1/5, which is 0.2. So that would be my curvature for the first bit. And then the curvature at the next bit for t equals 1 would be 0.127, 1207, 0.0477, and 0.02027. So I'm going to go put those values right in here. So this was 0.2 because that's what 1/5 is. This is 1207. This was 0.0477 and 0.0203. So you'll notice the curve is flattening out. So as we move away from 0, or actually from t equals 0, wherever that point might be, which I actually think was the origin in this case. If you put it in the original function, you'll see it's the origin. So as you move away from t equals 0, the curvature decreases. In other words, it's quite curved near the origin, right? So here's the origin right here. So it's quite curved near the origin, 0, 0, 0, but at the point 3, 1, 1, which I'm getting, by the way, by taking t and substituting t equals 1 back into the original equation. So matter of fact, I'm going to put points right here so that way you can see. So that one's 3, 1, 1. This one would have been 6, 4, 2. And this one would have been 3 times 3 is 9. 3 squared is 9, 3. So these are the points along the curve as you're moving through the curve. And as you move away from the origin, the curvature decreases. So the curve is flattening out. Okay, well, let's also think about the radius of curvature at the same time. So the radius of curvature is 1 over kappa. Right, so this is kappa, this is 1 over kappa. So, and it looks like a k, but it's technically not. So this would be 1 over 1/5, which is 5. This would be 1 over 0.1027, which is 8.26. I don't remember if I found these with Maple or with a calculator. Let me go see. Nope, looks like I found them with a calculator, which is fine. So I just took 1 and divided by each of those numbers. So I got 8.26, 20.96, and 49.26. So it's quite flattened out because at the origin, the largest circle I could fit in that would be tangent would have a radius of 5. So it's got a pretty tight, all things considered, for this curvature. But as I move out and move towards 993, I could fit a circle of radius 50 practically and just have it touch. That's the largest circle I could fit and have it be tangent, which is quite a large circle. So the curve is losing its curvature as you move away, which you can see when you look at Maple. You can look at the points on this. You can see where you're heading towards. I've got it rotated around, so with me here. So as you move into the origin, there, looking at it that way, it's got quite a bit of curvature near the origin. But as you move away from the origin, over here, or over near the top, near the word where it says thickness, the curve up there is quite flat. That's what you're discovering, right? That as you move away from the origin, the curve is flattening it out. It technically works in the other direction also, but we only did the t equals positive direction. And that's what the number kappa shows us. Kappa is showing us, and by its same token, the radius of convergence, or the radius of curvature, excuse me, are showing us that this curve is quite curvy close to the origin. And as you move away from the origin, that kappa, that curvature value is getting smaller and smaller. So kappa measures the curviness of the curve. Curviness of the curve, that's funny, right? And then by its same token, it gives you the radius of that curvature because they go hand in hand.